Hello and welcome to yet another video of Cornerstones of Math. In this video, I am going to talk about what is called indeterminate forms of limits. Basically, if the limit is given in one of these 7 forms, then we cannot say definitively what the value of the limit is unless we change it into some other forms. More specifically, 2 limits having the same form can result in different values. Therefore, when dealing with these 7 types of limits, we must find the values of those limits case by case. In this video, I will quickly introduce all 7 types of indeterminate limits by providing some of the easiest and most famous examples for each type. That sounds fun, so let us jump right into the first type. First type, the infinity over infinity form. You cannot say that the value of the limit is 1 or 0 or infinity right away. You must change the given expression into another form. Consider this simple limit, which many of you may have learned at the very early stage of the basic limit class. Many of you might already know that these types of limits converge to the ratios between coefficients of the highest power, but this famous rule actually follows from this. We divide the numerator and the denominator by the highest power term, in this case x squared. Then we have the limit of 2 plus 3 over x squared divided by 3 minus 2 over x. And these two parts are now in constant divided by infinity form, which is determinate form. This limit always converges to 0. Therefore, we obtain the limit value 2 plus 0 divided by 3 minus 0, and that's why the limit converges to the ratio between leading coefficients. As for the next example, let us consider these 4 limits, all in infinity over infinity form. However, despite having the same form, their behaviors are quite different. As for the first one, let us divide by 2 to the power of n, then we obtain the limit of 5 over 2 to the power of n plus 4 over 2 to the power of n divided by 1 minus 3 over 2 to the power of n. Here, these parts approach 0. However, this 5 over 2 to the power of n goes to infinity, so the entire limit diverges to infinity. As for the second one, dividing by 2 to the power of n gives 1 plus 4 over 2 to the power of n divided by 1 minus 3 over 2 to the power of n. As these parts approach 0, we obtain the value 1. As for the third one, we divide by 5 to the power of n to obtain 2 over 5 to the power of n plus 4 over 5 to the power of n divided by 1 minus 3 over 5 to the power of n. Here, since 2 over 5 has an absolute value less than 1, this part converges to 0, hence the limit is 0. As for the last one, we divide by 2 to the power of n again, then we obtain negative 5 over 2 to the power of n plus 4 over 2 to the power of n divided by 1 minus 3 over 2 to the power of n. Notice that the absolute value of negative 5 over 2 to the power of n gets bigger and bigger, and because of this minus sign, this term also alternates signs. Therefore, it diverges, or more specifically, it diverges by oscillating. The third example is the comparison of growth rates between algebraic functions and exponential functions. That is, when n is a natural number, let us investigate this limit. We have to use the famous L'Hopital's rule, which I will just denote as L throughout this video. Then we obtain n times x to the power of n minus 1 divided by e to the power of x. And if we use L'Hopital's rule again, we obtain n-1 x to the power of n-2 divided by e to the power of x. And we go on and on until the power of the algebraic function becomes 0. Then, all that is left on the numerator is n times n-1 times n-2 times 2 times 1, while in the denominator, the exponential function e to the power of x is still preserved. Therefore, the limit is 0. That is, we arrive at the important conclusion, which is that exponential functions increase faster than any increasing algebraic functions. And since we have dealt with exponential functions, it is only fair if we also compare the growth rates between algebraic functions and logarithmic functions. That is, when r is positive, now we consider the limit ln x divided by x to the power of r. By also using the L'Hopital's rule, we have the limit of 1 over x divided by r times x to the power of r minus 1, which is equal to the limit of 1 over r times x to the power of r, which gives 0. This means that logarithmic functions increase slower than any increasing algebraic functions. And now let's move on to the second type of indeterminate limits, the infinity minus infinity form. Here we cannot just say that the limit is 0. We have to examine each limit. Perhaps the most famous example appearing in many textbooks is the difference between functions that usually involve radicals. As for this specific example, we multiply a sort of conjugate expression, which is square root of x squared plus x on both numerator and denominator. Then we have the numerator becomes x squared plus x minus x squared. So this divided by square root of x squared plus x. So it is the limit of x divided by square root of x squared plus x. So now the limit is in infinity over infinity form with degree 1 on both numerator and denominator. Because this square root makes this degree 1 polynomial. So we divide by x, which gives the limit of 1 divided by square root of, and the inside must be divided by x squared, so 1 plus 1 over x plus 1, which gives the value 1/2. This next example is kind of advanced, but I decided to include in this video because it is actually quite famous. It is the famous mathematical constant called Euler's constant or Euler-Mascheroni constant, defined as the limit of the difference between harmonic series and natural logarithm. You may know that both harmonic series and natural logarithm diverge, but their difference is known to converge to a certain value and denoted as gamma. The proof of the convergence of this limit is not covered in this video because it utilizes some advanced concepts, and maybe I will cover that topic in the future. For now, let's move on to the third type, 0 divided by 0 form. This is another very famous indeterminate form that appears many times in basic level textbooks, such as this fraction form, which usually can be solved by factoring, or in a radical form, which can be solved by multiplying the conjugate expression, in this case square root of x plus 1 plus 1. But perhaps the most famous limit of this type is this, the limit of sine x divided by x as x approaches 0 equals 1. This limit does not have a universally accepted name, but I still want to call it the very important limit. The proof of this limit is also very important, but it takes too much time, so it's omitted here. You look it up if you want to. It's very famous, hence you can easily find it. Another famous 0 over 0 type limit that appears on basic textbooks involves the exponential function, which you can easily evaluate using L'Hopital's rule. It is the limit as x approaches 0 of e to the power of x divided by 1, hence it is 1. The fourth indeterminate type is 0 times infinity form. In a high school level, this form usually appears as the product of two rational functions where one goes to infinity while the other goes to 0, which usually can be solved by reducing to the common denominator. If we calculate this, we obtain, because this numerator becomes minus x, it can get cancelled, so it is just the limit of negative 1 divided by 2 times x plus 2, which gives negative 1 over 4. Another famous one is the limit of x ln x as x approaches 0 from the right. This is another famous example of applying L'Hopital's rule. Just change the function into ln x divided by 1 over x and apply L'Hopital's rule. Then we have 1 over x divided by minus 1 over x squared. So it is just the limit of minus x, which gives 0. The next type is 1 to the power of infinity. Be careful not to be confused though. This means that the base is not exactly 1, but only approaching 1. And we cannot say that the limit will be always 1 or always infinity for this type. Perhaps the most famous example of this type is the limit that gives the constant e. The limit of 1 plus 1 over n to the power of n as n goes to infinity gives the value e. It is also known that the limit of 1 plus x to the power of 1 over x as x approaches 0 also gives the constant e. And at this point, I would like to take a look at the limit which was already presented in example 3-4, which is 0 over 0 type limit. In part 3, I found this limit using L'Hopital's rule, but you can also find this limit by converting into 1 to the infinite form and using the limit for e. The trick is to make a substitution e to the power of x minus 1 equals t. Then x is given as ln 1 plus t, and as x approaches 0, you can notice that t also approaches 0. Therefore, this is equal to the limit of t approaching 0, t divided by ln 1 plus t, which gives 1 divided by 1 over t times ln 1 plus t, which equals 1 divided by ln 1 plus t to the power of 1 over t, and this part right here is in 1 to the power of infinity form, which converges to e. Therefore, the value of this limit is 1 over ln e, which is 1. The next type is infinity to the power of 0, such as this example. This looks very similar to the limit definition of constant e, but here x approaches infinity instead of 0. To find this limit, we can just take a logarithm on the limit, which gives ln 1 plus x divided by x, and then apply L'Hopital's rule, which gives the limit of 1 over 1 plus x divided by 1, which gives 0. This means that the value of this limit is 1. Or you can do it by changing this base 1 plus x into e to the power of ln 1 plus x to make the limit e to the power of ln 1 plus x divided by x, and then apply the L'Hopital's rule on the exponent. So we have e to the power of 1 over 1 plus x divided by 1, hence e to the power of 0, hence 1. And the final indeterminate type, the infamous 0 to the power of 0, which sparked many heated discussions and controversies over the internet. Perhaps it is best if we just dive straight into this example, limit of x to the power of x as x approaching 0 from the right. The limit itself is not that difficult. Just like the previous one, we take logarithm on the limit, which gives the limit of x ln x, and we have already solved this limit. Just we write ln x divided by 1 over x and apply L'Hopital's rule. We obtain the result 0, meaning that the limit of x to the power of x as x approaching 0 from the right is 1. Or just like in previous example, you can change the base x into e to the power of ln x. So you obtain e to the power of x ln x and proceed in a similar manner in the exponent. And this is the good place to discuss a little bit about the confusion people have towards 0 to the power of 0. Strictly speaking, the value of 0 to the power of 0, where the base and the exponents are both exactly zeros, is undefined. There exists no such number. When it comes to limits, we are dealing with the case where x is approaching 0, that is, having non-zero values all the time. In this case, we can find the value of 0 to the power of 0 type limits. However, in some cases, we define the value of 0 to the power of 0 as 1, just for the sake of convenience or for the universal consistency of many formulas. That is, in some cases, 0 to the power of 0 is defined as 1 because of practical reasons. But enough of this, because I would like to give you one final example of 0 to the power of 0 type limit, which comes from the Stirling's approximation, the famous approximation for factorials, so it can be handled more easily in terms of algebra. If you rearrange this formula, you obtain this expression, which is equivalent to this limit. And this right here is 0 to the power of 0 type limit. As for the proof of this limit, somebody already made a really good video about it. I will put the link in the description so you can go watch it. But this video has come to its end. I hope this video helped you understand more about indeterminate forms in limits, and please hit that like button if you enjoyed this video. Thank you for watching, and I will see you in another video.